Hello, so my name is Professor Bill Buchanan, and I run a podcast series on world leaders in cryptography. And I'm so happy to be joined by Kurt Rohloff. Hi, Kurt.
Hi, Bill. Happy to be here. Glad to be your guest, and always happy to kind of talk about some, really important and interesting topics in cryptography. So, thank you.
That's good. So, for those who don't know Kurt is an associate professor of computer science at the New Jersey Institute of Technology, NJIT, and a co-founder and CTO of Duality Technologies. He's also a co-founder of the open source PALISADE homomorphic encryption software library and a co-founder of the OpenFHE library. Kurt has an extensive background in areas of lattice cryptography and homomorphic encryption. And if anyone doesn't quite know Duality Technologies, then they might know the other co-founders, including Shafi Goldwasser from Berkeley and Vinod Vaktunathan from MIT. So it's quite an amazing cast of people that are involved in founding this company. So, what's your current role, and what does a typical day involve for you?
Sure. No, that's a great question. And, I joke about a few things with my friends and my wife and my coworkers that, the nature of being a CTO for a company like Duality and kind of doing what I do, it's like every day there's going to be an emergency. I never know what it's going to be, but it's kind of like the normal behavior. It's the daily emergency. It's kind of what it is. Um, but typically, what we do is Duality is a company. It's right now it's about 50 people, give or take, and we have offices in Tel Aviv and here in the U.S. and New York City, and we also have footprints in kind of a few other geographies also. Like we're very active in the UK, are very active on the West Coast also. And so my usual kind of routine is, wake up very early, 6 or something like that, and kind of scan the email almost immediately to kind of see what's kind of like the pressing issues that kind of emerged overnight in points east for what they are. And it's kind of the typical, I usually have most of my mornings kind of doing coordination with my colleagues in Israel and the UK and the East Coast. And as kind of the day goes by, I usually like to have blocks of days kind of towards the end of the day where I can kind of do kind of things that are not just meetings and kind of talking with people, but a little bit of writing to kind of think about where things go, position papers. Um, the role of a CTO is very multifaceted, in that there's some CTOs who are very focused on, basically almost like a VP of engineering. They go run and build teams and build code and things like that. And I'm kind of a little bit of a different CTO where I do a lot of outward bound things. I like to meet with our customers a lot to kind of understand what their needs are, kind of explain the technologies to them, and kind of support our go-to-market team. I also really focus a lot on community. And, as you gave my intro, open source is a huge thing for me. I think cryptography needs to be transparent, and to be transparent, it needs to be open. And so I do spend a lot of time not just on open source, but also work with standards communities and even talking with regulators and policy experts in various governments to kind of explain the value of open and open cryptography kind of for what it is. So there's a lot of things I tend to juggle. Never enough hours in the day, but it's just how it is. I love my job. I also joke that sometimes, being your own boss is kind of a fun thing, but your boss is still a jerk when you're your own boss is kind of how it is also. So and I know it's a very long-winded answer, but hopefully that kind of gets to it a little bit. So
Yeah, I think it's so important, and I think too often cryptography is kept within a closed community, and it's computer science academics talking to computer science academics, and really we need to break out of that and start to look at all the different domains where digital trust could actually help build a better and more trustworthy world. So if we wind back to your school days, what were you like at school? What were your favorite subjects?
Oh, so I was an electrical engineer by training. I actually come from an engineering family, and so it was kind of almost preordained. But I just I loved math. I loved physics. I loved the engineering courses, like the hardcore courses you would get, like statics, dynamics, circuit design, and things like that, kind of for what it is. And my experience of being an undergrad student in engineering was, yeah, you learn a lot of like equations and kind of methods and things like that. But what I loved about engineering education that I had was it was almost like a method of thinking, like a decompositional bit of thinking. Like, hey, you have a big problem, poorly designed, break it up into smaller parts and figure out how those smaller parts kind of get into the larger whole. And that kind of method of thinking, although it's not explicitly expressed that way, is almost like the way it was kind of taught to me. And when I was undergrad, and happened to be at Georgia Tech, one of the engineering schools in the U.S. I went on to grad school, and I was very focused on this area of electrical engineering called control engineering, which is basically how you design control systems for like planes or networks or rockets or the kind of things that kind of fly around where you need something to kind of adjust dynamically. I got very interested in embedded systems when I was in engineering school at my PhD. And I ended up getting very interested in theory of computing to kind of see like what kind of circuits we could put on the smallest hardware possible, kind of for what it is, and what kind of software we can kind of put on minimal memory. And so I got very interested in theory of computing somewhat laterally, for trying to design embedded systems. Um, the way of the world, I'm of the generation that was getting my engineering PhD during the 9/11 attacks. And so I went fairly soon afterwards into defense industry. And kind of the way life is, it just, happened to be kind of an area that I felt very passionate about also, and started learning about security and cybersecurity and things like that, kind of as it is. So it's a little bit of a, education and a little bit more, but that's kind of where I came from at some level. So.
It sounds quite similar to my background. I come from an electrical engineering background. I studied electronics. I saw the wonder of the transistor and the integrated circuit. I moved into network data communications and then networks, and then cybersecurity is just a natural move into that. So what sparked your interest in cryptography? Where does the first line of cryptography start for you?
Fairly early on. So my first real job outside of grad school, I happened to be at a company that at the time was called BBN Technologies.
Oh, I remember
Where,
BBN. They were the
yeah,
creator of the first router,
yes,
packet
yes, yes.
switched. They won
So
the contract from DARPA, as I remember. It's a long
yeah, they
time ago.
were. Yeah, no, it's one of these seminal technology
Yeah.
companies outside of Boston. Um, where as you just rightly said, that they did a lot of the earliest work on the internet. And so I happened to be dropped into a place where a lot of people were doing a lot of very foundational network design, and also cybersecurity work. BBN happened to be a place that did more work for DARPA than pretty much any other place in the world. I think even more than Lockheed Martin at the time, a big defense contractor. And BBN was only about 700 employees, and so we were doing some pretty interesting stuff for the U.S. DoD as part of the national security mission. I happen to be fortunate. I was dropped into the group that was doing distributed computing work. They happened to have a program manager who was a control theorist, and they wanted a control theorist, and I just happened to be on the market at the right place at the right time. And as I jokingly say, sometimes it's better to be lucky than good. But yeah, it was wild. I knew Ray Tomlinson, who
Ah,
invented email. He had an office
wow.
down the hallway from me, and we used to drink beer on like our Friday kind of good TGIFs and things like that. And so yeah, I knew a lot of the kind of early founders of the internet, and so it was really wild to kind of hear the early stories about like no cybersecurity, then like hey, this is a problem, and then seeing how they were starting to adjust and kind of bring it into the like both early internet and the modern internet at the time, right?
Yeah, because I remember it was seen to be an extended campus of MIT. Is that the right university? They were looking to headhunt the best from
Yeah.
MIT.
So yeah, the history of technology in Boston is as you said, it's kind of Harvard, MIT. BBN was kind of out on the edge of the border of Cambridge, tucked away a little bit. But yeah, it was founded by two MIT architecture professors. And a lot of the early recruits were MIT grads and things like that. Boston had a very active tech scene, in the 60s and 70s before the Silicon Valley became a thing. And so there was a lot of places like DEC and Wang Computers and things like that were kind of all in the same neighborhood, which was, like I said, now is ancient history. Well, these companies were acquired, but there was also a very big defense industry there between Lincoln Labs and Draper and a lot of other, Alpha Tech and a lot of other kinds of very advanced tech companies. So yeah, it was always, we used to jokingly say kind of the third campus, although it was a very kind of specialized kind of, tech school kind of for what it was. And it was phenomenal because, we were doing, this really kind of advanced stuff for DARPA. But this kind of gets to the other side that I'm very passionate about is not just research for research sake. It was really focused on things that could, create an impact over 2, 3, 5, 10 years. And this notion of advanced technology transition was kind of baked into the culture. And this is kind of what I've tried to do in my career also. I really kind of taken it to heart is, yeah, you can kind of go do cool things and whatnot, but you really kind of want to solve some problem, which is, in part of the DARPA culture, part of the BBN culture, and these other things that I've just internalized. And I do try to kind of push and push that way. And when I choose to take on research projects as it is. So,
That's excellent. Okay, so obviously you can't tell us in great detail about what your markets and what your customers are, but what's the core focus of Duality?
sure. No, happy to talk about this and happy to kind of talk at length. Duality inherently, we are a software product company. We're a venture-backed technology startup. We focus on the problem of secure data collaboration. Up to now, the vast majority of data sharing, particularly sensitive data sharing, has been protected by legal agreements, things like MOUs, data use agreements, things that are expensive to put in place because lawyer time, things that are kind of complicated once they're in place. And they're generally out of reach for small and mid-sized organizations. Effectively large companies like, large hospitals have, almost but not quite infinite lawyer time, but smaller doctor offices, and things like that don't have easy access to this. And so it's very hard, for example, to securely share, patient data and things like this. And we kind of have this kind of focus. One of our main focuses is on the focus of rare diseases and rare disease analytics. So a rare disease is a disease that affects basically a small percentage of the population. 1%, 0.5%, I forget the exact details, but it's something of that scale. And the challenge with rare disease is that, any one doctor, any one clinician might see any one specific rare disease once in their career. And the challenge with rare diseases is that if you take the collection of all rare diseases over any reasonably large country, UK, US, Germany, anything like that, rare diseases are shockingly common, like on the order of something like 20% of the population, US, UK, wherever, population has a rare disease or will have a rare disease at some time or another. So you have this huge population of people that are at some time in their life going to be dealing with a disease that is completely underserved by medical science, specifically because organizations can't share data to aggregate the data across the population of patients with rare diseases to get better insights on, leading indicators of hey, you're going to have this thing, make adjustments in lifestyle, indicators of what, pharmacological interventions will affect the outcome of this disease so it's not so severe, or other kinds of diagnostic or prognostic type behavior. And so we have this vision of, can we provide software that allows organizations, for example, to take data, encrypt it, aggregate it, share it, and allow researchers to build better models of things like disease progression, some sort of analytics of what kinds of, genetic mutations are indicative of rare diseases and other kinds of things that lead to, fundamental social good of better health outcomes for the population as it is. So.
That's excellent. I completely buy into that. We have research going on here in Scotland that's actually looking at that type of work. And it's really how you can protect citizen privacy, but also to be able to use the data in a trustworthy way. And obviously, homomorphic encryption gives us that opportunity. So, what's the history of the PALISADE library, and how has it developed into OpenFHE?
Sure. No, happy to talk. It's been a bit of my life's work for the past 15 years. As I kind of shared before, I used to be at BBN. I used to still do a lot of work with DARPA. Um, and around 2009 timeframe, I heard a bit of gossip from one of my colleagues about this new kind of breakthrough called, homomorphic encryption. And at the time, I was taking, and this is benefit of being in Cambridge. I was taking a night class at Harvard about cryptography of all things. And so I kind of played with cryptography and networks for network security, but I decided finally to take a class at Harvard kind of at night. And it happened to be the same time I was taking a section on really kind of basic, non fully homomorphic cryptography. And it was interesting. And I also kind of heard that one of my colleagues at DARPA was thinking about starting a project in it. Um, and as you're probably aware from your background in electrical engineering, a lot of the fundamental math of fully homomorphic encryption is based on lattice cryptography, learning with errors, ring learning with errors. And the underlying mathematical constructs are very, very similar to what one does for large scale control system design. Dealing with large matrix operations, things that look like Fourier transforms, things like that, things that I've kind of knew how to do my entire career, and kind of get them working really, really fast. And so it kind of gets to what I said before. Sometimes it's better just be lucky than good. But I kind of, my colleagues and I went to go speak with a DARPA program manager who was interested in this, and I ended up putting a bid to kind of run an implementation team for homomorphic encryption for DARPA in 2010. And lo and behold, we won the contract. I was running the team, and it was really, really great. So we were running a team. I was starting to work with my longtime research partner, who just retired this week, Dr. David Cousins, who was kind of behind the scenes throughout all these years. But I was also working closely with Chris Pikert, who was my subcontractor and was at Georgia Tech and now is at Michigan, and kind of done some other really amazing things. And we were building the first implementations of homomorphic encryption. And Craig Gentry and Shai Halevi did some really early work at IBM with first implementations. And we were contracted with DARPA to basically try to make it go fast, throw it in on FPGAs and see what we can do. And it was wonderful. It was like a who's who of modern cryptography was on that program. I met Shafi Goldwasser there. I met Vinod Vaikunthanathan. Avi Shalat was there. The guys from UCLA were there, and Dan Bonet, and it was like everyone who was everyone in kind of the U.S. Doing modern cryptography was there, and it was just amazing. Especially for me, taking a class at night school at Harvard, kind of meeting these folks whose work I was reading about, like at night, kind of what it is. Um, we were building homomorphic encryption, and we started to design this first library at the time in 2010 called Cypher, which never went public. But we were basically improving the runtime of homomorphic encryption by an order of magnitude every 6 months. And it was like, Moore's law just kind of juiced up a little bit. And at the time, we were looking at early applications for homomorphic encryption. And one of the early ones we kind of settled on was how we can do voice over IP signal mixing. And so we had this demo that we were putting together where we were basically putting what was one of the schemes that's no longer used, the LTV scheme, on stock iPhone 5Ss. And we chose the iPhone 5Ss because it was the first iPhone that had a 64-bit processor, which means we can kind of do more math natively, larger word operations natively on that processor. And so we had this demo that we were running where we had someone in DC, someone in Boston, and someone else in a different part of Virginia, talking into iPhones, and the audio with the microphone. We had a custom vocoder that would translate the voice into bits and bytes and whatnot, and then run homomorphic encryption to encrypt it, send the signals up to basically the really cheapest Amazon servers, like pennies an hour over commercial 3G networks. And then we can have audio quality, teleconferencing, multi-party with mixing and everything else, all simultaneously at line speed. And I frankly drank the Kool-Aid on the tech at the time that we could actually get homomorphic encryption working well enough. We could actually have reasonable conversations like we're having right now, at real time. Um, so I decided I really wanted to kind of focus on this, and kind of the nature of DARPA work up till then for me had been, you win a project, you do, as best as you can for 4 years, and you find the next project. And I really wanted to continue homomorphic encryption, like to use a bit of an American expression. I really drank the Kool-Aid on it. And I tried to sell my CTO at BBN, like, hey, this is going to be an amazing thing. Let me go do it. And he effectively told me that if you really want to do that, you got to resign and kind of start your own company. And so it was basically like, okay, well, here's my resignation letter. I'll see you later. I have a very fond spot for BBN, but privatization is not something that it does. So I was basically, I don't think that technology was ready enough to kind of build a company. And Shafi and Vinod and I were talking, and we met up with Rena Shansky, who's another one of our co-founders, who was a venture capitalist in Israel. And Alon Kaufman, who's our CEO now, was a former head of RSA Labs, another kind of very important organization in cryptography. And so I landed at NJIT because the dean at the time for computer science, Marek Rushinkevich, he was also part of the DARPA community. He wanted to kind of grow NJIT's ability to do defense work and kind of go after DARPA funding. And so he recruited me to come to NJIT. And I loved it because I could go and work on things. And I was able to arrange a little bit of money from DARPA to kind of go hire some people and start building this open source library. It's also a small world that, like, basically my first week, I ran into a gentleman by the name of Yuri Polyakov, introduced to me by the dean, who is become like my research partner, very close friend and research partner. And we've been working together. We had that first meeting, and we've been probably talking like every other day for about 10 years, kind of ever since. And so he and I co-founded PALISADE. We did a lot of DARPA work together. He's now my VP of our VP of cryptography at Duality. And we also co-founded OpenFHE. And I think he's going to be a guest on this podcast also fairly soon. So yeah, we have this kind of very deep bench of people at Duality. And PALISADE was some of the early work we were doing for DARPA to really kind of focus on things like actually program obfuscation of all things. And so we kind of did a little bit of a side hustle over there for a little bit, and, happy about the work, but the vision was always homomorphic encryption. And the challenge that we saw was a lot of the early work that was being done by, the work at DARPA, and we also HELib and SEAL was kind of out at the time from IBM and Microsoft respectively. Is I really wanted to kind of come at it with like a production mindset, like, hey, I want to use this for the company eventually. Let's build it from first principles. And Yuri was just absolutely phenomenal at kind of putting all the bits and pieces together in the library and doing that. And we also always knew that if this homomorphic encryption were to be real, we needed to build community around it. And so I spent a lot of time with Shai and Kristen Lauder, who was then at Microsoft, and Kim Lina, who is still at Microsoft, and Craig and Yuri, basically founding this homomorphicencryption.org industry consortium to start to kind of advocate for policy and policy acceptance and standard acceptance around homomorphic encryption also. So it really has been, a life's passion in many ways for a long time also. So I know that's a very long-winded answer to a very simple question, but so it is, right?
That's excellent.
Yeah.
I've evaluated the OpenFHE library, and it's far beyond anything. SEAL seems to have stopped any development, and Microsoft have kind of given up on pushing it forward. But OpenFHE, I say to any researcher who's out there or any developer, if you're interested in homomorphic encryption, that's a place to be. I think the communication that goes on, the support from the community is really excellent. So I know it's like trying to pick your favorite child, and but what's your favorite paper that you've ever published and why?
My favorite published that I've ever published. That's an interesting question because when we had the very first PI meeting for Proceed, which was the very, very first DARPA program in homomorphic encryption, this is the first time I met Craig Gentry. He was on it too, actually. I forgot. And here it is, the gentleman who you basically wrote the first seminal paper, homomorphic encryption. And as an icebreaker, we were asked to kind of go around and talk about our favorite paper. And Craig gets up and Craig's like, well, I published these papers and I put them out and I'm always a little embarrassed because I want to do them better again, kind of for what it is. And I thought it was like, he is such a gentleman. He is
Yeah.
such a wonderful person. He's so humble. And it's almost like, that's going to be my stock answer kind of for all time. But then again, I have had a few that I have liked a lot. And so I'm not as humble as Craig, I guess, kind of for what it is. There was some very early work that I was involved with, probably my first real homomorphic encryption implementation paper,
Mm.
which was how we do the voice over IP processing. And it was published in the IEEE transactions. I forget which transactions, but that was something I was very, very, very proud of, and kind of like, a real world application of homomorphic encryption. It was running on the open source Mumble Murmur clients for voice over IP, and that was kind of like, changed my life fundamentally to kind of go focus on these things. And then there was a series of really good papers that I hadn't necessarily, I don't think I was an author on, but I was kind of on the periphery. And this is more work that Yuri was doing. And so his name's on it, my name's not. And I'm not taking any credit at all for the work. But like I said, I was on the periphery as kind of like the CTO when this was going on. And Yuri put out some fundamentally just wonderful work looking at applications of homomorphic encryption for medical research, in collaboration with Dana-Farber Cancer Institute, that was published in the Proceedings of the National Academy. So, if I could say, you could broaden this out, not my favorite paper personally, but my favorite paper that kind of came out of the OpenFHE duality ecosystem were these two papers that Yuri wrote on the Proceedings of the National Academy for cancer applications of homomorphic encryption data sharing, as it is. So,
Excellent. Yeah, I think was it Phil Zimmerman who tried to create, the PGP creator, um, Zimmerman, was it Phil?
that rings a
And
bell. Yes. Yeah. Yeah.
yeah, I
Yeah.
think he created a protocol for voice over IP with encryption. So it's still probably an area that hasn't been solved yet. That overhead is still a bit too much when it comes to real-time communications. So, in terms of homomorphic encryption, could you explain it in a simple way? How would you explain it to a 12-year-old child, for example, or a politician?
Yeah, I get this question a lot, and there's never a good enough answer. There's lots of answers. The way I like to describe it is kind of like, um, there's how does enable computing, and the way I like to think about it is, kind of like, the magic of kind of digital encoding, kind of for what it
Mhm.
is if people ask that how we can get this work, it's kind of like, we have these magical devices, phones that we carry around in our pockets. And what we can do is that we can speak, and we have these sound pressure waves coming out of our mouths, and it hits a microphone, and data gets digitized and converted. And basically, eventually, this time series signal gets converted into a frequency domain representation. And so this is more of an electrical engineering explanation of homomorphic encryption. And this notion of, encryption basically is a lot like taking a signal from time domain to frequency domain. And because once you're in frequency domain, you can still do a lot of the same processing, filtering, and other kinds of operations. It just like that, multiplication looks like convolution, and addition still addition, and things kind of like that. But you can have this different representation of the same information, which is like sound waves in my voice, represent it digitally and still do compute on it. And I like to analogize, basically draw parallels of homomorphic encryption, of taking data, and translating it to a different representation. You can still do compute on it, just the compute looks very different overall, similar to like I said, this magic of digital signal processing and things like that, that we carry around in our pocket as it is. So maybe I didn't quite hit the 12-year-old or politician level, but hopefully
Yeah,
that is at least a start.
I
So
understand that completely. I remember doing
yeah,
convolutional processing, and it was really difficult. In the time domain, things are really difficult, but in the frequency domain, things become easier. But
yeah,
obviously, your signal has changed, and you don't see the detail of it. So I understand the analogy completely. So obviously, what we add noise onto the vector. So we have this massive lattice that we create, and then we add a little bit of noise, and we do our processing, our scalars, and our divisions, and polynomials, and so on. But obviously, one of the problems is that this noise is adding up all the time, just like in an electrical circuit. Every circuit that you go through will add noise, especially if you're multiplying. So, could you give us more detail on what the bootstrapping process actually does within homomorphic encryption and why it's so important?
sure thing. So yeah, no, you hit the nail on the head of a lot of the the bane of existence of applied homomorphic encryption, which is basically that in order to secure data, we, this is hand waving, as you know, but we basically embed data in noise. We embed it in a certain way that we kind of extract it later with the decryption key. The trouble, and this is kind of like going back to engineering analogies, if you take two approximate measurements and you add two approximate measurements together, well, your approximation error grows. If you multiply two approximate measurements together, your approximation error grows even more. And so the trouble with homomorphic encryption, as you laid out, that as you do computations, doing additions and multiplications and other types of operations, the noise gets larger and larger and larger and larger. Um, and what Craig Gentry's fundamental insight was a way of doing bootstrapping so that you could, in some sense, refresh a ciphertext. And when homomorphic encryption came out was around the same time that this movie, science fiction movie called Inception came out. And the concept of Inception is basically, dreams within dreams within dreams and whatnot. And you could do things inside one dream that has implications for other kinds of, dream states. And, I almost think about bootstrapping homomorphic encryption as kind of like the inception of cryptography at some level. And that what you do is that you have an encrypted ciphertext with a pile of noise. Well, one way of stripping away that noise is by doing decryption. Fundamentally, the noise kind of washes away as long as the noise isn't too large. And so the kind of the inception, trick that I believe Craig had was that you could basically have this noisy ciphertext encrypted again, and then homomorphically run the decryption circuit so that the inner ciphertext basically dissolves away, and you have the data with an additional set of noise around it, but the inner noise is basically washed away. And so it's a way of effectively resetting the noise on the inner ciphertext, so you only have the noise on the outer ciphertext, kind of for what it is. And that's the way I generally try to describe it overall. It's basically like a homomorphic evaluation of decryption on a doubly encrypted ciphertext. And I know there's been a lot of advances in this area ever since, and this has been a major focus of Yuri and my other colleagues at Duality and other research teams too. But this is how I generally think about it, as a way of kind of stripping away this noise to kind of, in some sense, reset the ciphertext too.
Great. Yeah, excellent.
Yeah.
And so that apart from noise, what's the other drawbacks that we get with homomorphic encryption? How do you think we're going to overcome these?
Sure. So the other major challenge associated with the use of homomorphic encryption is that it has a very non-standard compute model. So you think about homomorphic encryption. You take a ciphertext, you have a pile of data. The fundamental data representation is vectors, and like I said, I am hand waving a little bit, but it's a vector processing type operation, which, okay, not that weird. We have GPUs and FPGAs that do vector processing. The challenge is that the fundamental instruction set enabled by homomorphic encryption are these two operations called eval add and eval mult. A few other variations too, but those are the two fundamental famous ones. And these eval add operations, they're like homomorphic addition in a polynomial, and then eval mult is basically multiplication in the ring, and so it looks a lot like it's to non hand waving, like a convolution with some extra kind of weirdness kind of baked into it also. And so what this basically means that if you want to do real computations with homomorphic encryption, you basically have to map what you want to do into these kind of different instruction sets, which are kind of very non-standard for traditional computer scientists. And the other analogy I like to use with it is kind of like using a bare bones homomorphic encryption library. It's kind of like buying a piece of silicon from Intel and then programming assembly. Like, yeah, you can do it if you really want to, but very few people can do it really well. And generally, you don't want to do it just because it's such a challenge. And so what we as a community have been trying to do, and Duality in particular, is basically layering software libraries on top of the fundamental homomorphic encryption. And so what we've been doing is, for example, designing Python libraries for four-function calculators, matrix vector algebra, statistical analytics, statistical operations, machine learning, and things like that. In our vision at Duality is, and this kind of also gets back to a little bit of my DARPA background, is that in order for advanced tech to be used operationally, it needs to be as boring as possible. And that it just needs to kind of drop in and work.
Yeah.
Because if you have like an operator, whether it's like a military person or a doctor, they don't want to have to care about cryptography and things like that. They have a way of working. They want to continue to work. And if you could take their software, rip it out, put something new in, and they don't even know that it's there, you've won. Then you have kind of an easy kind of seamless integration. And so our vision is basically software libraries that enable these kind of standard operations that we're familiar with, that mimic the kind of the standard NumPy, SciPy, scikit-learn, Python SDKs, or R or Rust, or kind of choose your favorite language. And so the challenge that we have is that to make homomorphic encryption run efficiently for these standard operations, you do have to do a lot of work about data structure optimization, algorithm optimization, also it can kind of look the same to kind of downstream users. And then, and it's kind of like taking code that was optimized for a CPU and porting it over to a GPU. It's a very different compute model, very different data structures, very different everything. And the first time you do that porting, it's never going to run faster. It's always going to be slower. And it takes a few generations of effort to kind of go and do that. It's very specialized knowledge. It's things that we know how to do very well at Duality. And it's a little bit of kind of the upwards cliff that people have to get on to kind of do homomorphic crypto well from bare bones. But our mission and what we're trying to do is make homomorphic encryption easy by exposing these higher level libraries that are easier to kind of integrate into our own products, others' products, and things like that, kind of for what they are. And so I see that notion of data structures and algorithm design sitting on top of homomorphic encryption as really being the major challenge with the application of homomorphic encryption in the short term.
I completely agree, and I can see we've built our CPUs with the 64-bit registers and the fetch executes, and really that's not the computing model we need for machine learning and for post-quantum cryptography and also for homomorphic encryption. And the world is moving towards an NVIDIA CUDA GPU world. I think Microsoft are
Right on.
building the biggest data center in the world just now that they want, and it's all full of GPUs, not our old servers that we used to have with these monolithic processors. So I think that is obviously going to be a great advancement as we start to move towards more machine learning, more homomorphic encryption. And I see the two fusing together. I draw a diagram of AI and homomorphic encryption, and the sweet spot is where they meet in the
Yes.
middle, and then you can have privacy aware and every bit, even though it's in the process and in the memory, is still protected. That would be the dream overall. So I think in the past you applied your research into genome searches. Could you just explain how homomorphic encryption works with a genome search?
Sure. Yeah, so there's a fair bit of work that we were doing over there, and kind of our two main kind of products as it is at Duality. One is secure query capability, and the other is the secure data science and analytics platform also. And the vision for the secure analytics platform, if this is what you're asking about, is basically how do we aggregate medical data from multiple locations? This kind of rare disease cancer analytics. We've had I've had both Duality, myself and Yuri, and have had a very long and very enjoyable partnership with a researcher at Dana-Farber Cancer Institute, in Harvard Medical School, one of the main cancer research centers here in the U.S. A gentleman by the name of Alexander Sasha Gusev. And he's a working bioinformatician, and he runs a lab at Dana-Farber where he has existing workflows about how he basically ingests genetic data to look at what mutations are indicative of certain kinds of rare cancers. And he's got all kinds of workloads at different levels. But the main one that we started looking on early on was what was called the chi-squared analytic. And basically, it's kind of like, and the way I'll describe it, very hand waving, and Yuri can go into very deep detail, of course, also, is it's kind of like kind of a variation of like a correlation analysis. You're kind of looking for kind of correlates of what mutations look overall. And so we had some funding from NIH, NHGRI, National Institute of Health, National Human Genome Research Institute. A nice lady, Heidi Sophia, was supporting us on this at NIH, and basically we're taking data from it was actually UK public data set. I forget, I'm drawing a blank on it right now. 1,000 Genomes Project, I think is what it was. And in fact, I know that's what it was. And so we were basically taking this public data and basically running through pipelines and workflows that Sasha, our partner at DFCI, gave to us. And so we were able to basically replicate some of his standard workflows running through a homomorphic encryption pipeline. And we've kind of done it also with similar things with Tel Aviv Medical Center and kind of a few others. And at some level, the earliest work that we were doing was showing that, like, hey, this is what we got through the encrypted method. This is what we got for the unencrypted method. It's the same, so it works at some level. And so that was kind of like, the kind of big epiphanies that kind of at the time that the stuff could actually be used for real world workloads, not just kind of made up problems calling for what they were. And so this was something I was very proud of. And like I said, Yuri wrote the paper on this, and with Sasha and kind of a few others. And this is one of the reasons I'm so proud of this work, and that it kind of came out of this Duality ecosystem, an OpenFHE ecosystem that we had. So
That's great. Yeah, I use OpenFHE a lot, and our PhD students are using it fairly extensively just now. But where does it go in the future? Is that development finished, or what are the open gates that need to happen?
no, that's a great question. It's kind of like saying, is Linux ever finished or something like that? No, so as I said, this is like the third generation of our fully homomorphic encryption library, from like the early Cypher, from DARPA Proceed
Mm.
days to PALISADE to OpenFHE. The trend that we're on is fundamentally building out community. The set of users that we're very proud of our community. I am over the moon that you're using it with your students. We have a lot of other users that are using it. We have a very active online forum. I couldn't be happier about the community that we've built up. Duality team members do spend time kind of on the forums answering questions. There's other people that are on there answering questions. And I had a bit of a kind of like a kid going to college kind of moment earlier this week. I was invited to kind of go sit on a panel at this IEEE conference called MILCOM in DC in a few weeks. And panel about FHE, applied FHE, happy to go. This is my job, and of course I'm happy to kind of talk about FHE at any time. And I was looking through the agenda for the conference, full on IEEE conference, and somebody was giving a tutorial about applied FHE, and I was like, okay, cool, I'll look at it. And it was a whole tutorial built around the use of OpenFHE for applications, built by someone I had no idea who, that was doing this kind of work, kind of for what it is. And I was like, hey, people are using it, and it's not just my friends and family; it's actually like out in the world. And I couldn't be happier about that. And so, like the big trend, the continuing trend for us with OpenFHE is building out ecosystem, building out community. Not just getting people to use it, but getting people to engage, contribute software back, and going forward from there. The other side of it also, and this is a little bit broader than OpenFHE, is pushing on policy acceptance, regulatory acceptance of the technology. One thing that's been really nice is the current person who's in charge of OSTP, the Office of Science and Technology Policy, is a lady by the name of Arti Prabhakar, who was prior DARPA director, who was kind of funding my sponsor to fund FHE back in the time. And she's been basically, her office, OSTP, has been pushing forward on privacy technologies like the US UK collaboration for data sharing, and a lot of the ARPA-H things have been kind of flowing out of kind of the President Biden moonshot that have been kind of pushing on privacy technologies also. And so I'm seeing this kind of like groundswell of interest in policy and regulatory and standards like NIST and things like that around privacy technologies and homomorphic encryption. And I really want to help advocate for not just homomorphic encryption, but privacy technologies. But I do have a kind of a bias toward homomorphic encryption and OpenFHE as an accepted technology for solving these data collaboration challenges. And in fact, even ICO in the UK, the Information Commissioner's Office, which is a branch of the UK government, has basically put out studies and even position papers about the accepted use of homomorphic encryption and cited duality in our work of OpenFHE as an accepted use for doing things like fighting money laundering and financial crimes and things like that also. So I very much want to push on that and, not just community, but also acceptance of this technology more broadly as kind of like, yeah, this is the right way to kind of do things and it's a good way of going and do things. So yeah.
Yeah, I completely agree. I think the EU is really pushing forward in homomorphic encryption, and I think the EU wants to create these trusted data processors because it's a perfect marketplace that you can offload your data in encrypted form to whoever has the cheapest cloud resource who isn't being used. In fact, it's
Yeah.
as close to you as possible at the edge of the cloud, so you're not consuming all this energy. So I think there are a lot of use cases, and I think Cloudflare are now putting these edge GPUs near where they're required, so you can actually see a lot less energy being consumed as we push our processing out to the edge of the cloud and keep the privacy. Obviously, GDPR is a big issue in the EU, and it's very difficult to keep that privacy when you're dealing with data that reveals sensitive information. So one of the features that I think OpenFHE supports just now is proxy re-encryption. And I know you've published some work on this in the past. So can you explain how that works and what's the use case for it? I don't know if you'll be able to answer the use case part, but what do you see as possible use cases for that?
No, yeah, happy to talk to that. Proxy encryption has been kind of like, OpenFHE is definitely, and FHE in general has been the real focus of my professional life and the private life for going on 15 years now. Um, Proxy encryption is, I almost think about it as kind of like the little cousin or little brother of FHE in that it basically enables secure access delegation of information. And so a medical use case of it is, the kind of the nature of life here in the U.S. is, I grew up in one state, I went to college in a different state, I went to grad school in a different state. I've kind of lived in a few different states, for different jobs over my life. In every state, I've had a different doctor. And so as I kind of go about and live, um, it would be ideal if, my current doctor could access to kind of my prior, care providers' medical files on me, just to kind of have a more complete history because, hey, I'm only human. I can't remember everything, as it is. Um, and so the vision for proxy encryption, and this is kind of like I said, the medical vision of it, a medical vision of it, is that, hey, if I have a doctor that has my medical files, they don't necessarily need to store it like locally. They could encrypt it, sort of on a cloud. The challenge is that as I move, kind of as I go about my life, new doctors need access to those files. Is there an easy way to kind of share access to those files other than that my old doctor downloading, decrypting, encrypting it again, kind of sending it off in kind of a secure email? Um, so we were, saw proxy encryption as a way basically of taking data, encrypting it, sending it to a cloud a year, 10 years, some odd later, basically a way of delegating access to that file by basically generating something that's called a re-encryption key. Re-encryption key being generated by, cryptographic material from the secret key from the original source, a public key from the recipient, basically public key being sent to the source, generating a re-encryption key, uploading the re-encryption key, and the re-encryption key being able to basically switch the key of the information without decryption, without download and things like that, so that future recipients have secure delegated access overall. And Yuri and I have been working on proxy encryption basically as long as we've been working together. We always saw it as like a really cool thing. Like this has so many uses for access delegation and so many uses for kind of shared access to files. Even think about like a packet switched version of the internet encrypted by proxy encryption at some level. Um, and so we have been pushing on this, for better or worse, OpenFHE has been having much more uptake, than proxy encryption, but we've always had it in there, and we've always had this little bit of a party trick about how we use proxy encryption to kind of move files around and kind of use it as almost like underlying infrastructure for a lot of things that we do to do delegated access with end-to-end cryptography also. And so it's been a really nice tool, even if it hasn't necessarily gotten the full visibility of FHE. But I'm a big fan of it, and it is very compatible with FHE kind of for what it is. And I think it's great. I wish more people were aware of it because I think it solves a lot of problems with secure networking also kind of for what it is. So,
I totally agree. And we use delegation in our lives so much. We go on holiday and we delegate
yep.
work. We buy a house and we delegate to a solicitor. We trust the solicitor. The solicitor must now create the asset, well, move the asset from one person to the next. So that idea of delegation is so important in
Yeah.
our normal world. And I think for these technologies to be adopted, we need to understand that people trust some people on their behalf. And maybe it could be someone who doesn't understand how to use the bank account or something like that. There can be a delegation onto someone in your family. So it is a key part of our world, and we need to try and mimic that. And obviously, as you say, in a medical context, there is a lot of trust involved. That one-to-one relationship that you have with GPs is fundamental to the whole of your health and well-being environment. So the other area that I love within OpenFHE is your machine learning model. As far as I can tell, what you do, and please correct me if I'm wrong, is that you take a vector and you encrypt the input vector to the neural network with a public key. You then have matrix multiplications, which you can do within your libraries. And then on the output, you've got the layers of the neural network, and then the output, you use your private key. Obviously, you could use symmetric key, but it's not quite as nice to do that. But you then use your private key to decrypt. So all of the layers of the neural network never get to see any of the data overall. So could you say roughly how you see machine learning developing with homomorphic encryption?
Yeah, no, happy to. You know, machine learning was always seen as kind of like the killer app for FHE, even back at the very earliest days of 2009 and 2010, even before, Craig had his Craig did his seminal work also. Um, where this is going, and I'm going to actually kind of turn this question on its head a little bit to kind of talk about something that's adjacent, but I think it's super important for a research topic. Is what we see in practical application, with our customers, with our potential customers, is that there's a lot of need for machine learning, not just encrypting data that's kind of run through a machine learning model, not just encrypting data that's used to kind of train machine learning models, also to encrypt the models themselves, because sometimes the real IP is in the model. But generally people have applications for this, and sometimes these applications are you have an existing model, like in medical domain. Sometimes you need a model to be ported over to FHE, and it needs to have the exact same input-output map to 7 decimal digits precision, for clinical significance or regulatory acceptance, all these other kinds of things. It makes total sense. Sometimes for other kinds of applications, like fighting financial crime, other things like this, where you don't need the same input-output map. What you really need is something with as good, at least it's comparable, accuracy, precision, and recall, and things kind of like that also, where you don't need the exact same input output map. And then basically and practically what this means is that you have kind of two similar families of techniques that might evolve overall. They have a family of techniques that basically are used to basically port existing models to run exactly the same on OpenFHE or FHE in general. Or you also have the techniques for designing different kinds of machine learning capabilities that maybe not be exactly the same as kind of the classic convolutional neural nets and things like that, but provide similar kinds of performance in terms of accuracy, precision, recall, F measure, whatever kind of measures, metrics you want to use. And I do see a need for a lot of research in this area of FHE specialized or even just privacy specialized machine learning techniques. So, just because we found that neural nets work good, on unencrypted data, doesn't mean it's the best technique to use for homomorphic encryption, or whether support vector machines or k-nearest neighbors and things like that. And these things that were designed for optimization for CPU execution or GPU execution might not be well optimized for FHE execution. And so I would love to see, growth and research of FHE specialized machine learning models that are almost clean sheet design, not just variations of existing techniques, but clean sheet. And so, that's what we're trying to enable with OpenFHE is, providing a lot of these building blocks for this kind of broader vision, not just of porting existing models and making them secure, but enabling new things too also. So I know I didn't quite answer your question, but
No,
it's something I'm very
that
passionate
was
about. And I love
that
this research
that
vision. Yeah.
that was perfect. I mean, it's providing the Lego blocks that would allow us to create the buildings that we want. If you create the wrong size of Lego block as a foundation, then it's not going to work. And I think that's what you've provided with your libraries and your tutorials. They take it easy, and it's the first time I understood homomorphic encryption with machine learning. And because I applied it, I coded it, I could see my inputs were the same as my outputs. My little toy example works. So I think that's really brilliant. And cybersecurity has been built up with role-based security, and we know that's completely flawed when it comes to zero trust and so on. So, is there a place for attribute-based encryption within side's homomorphic infrastructures?
It is, that's a really interesting question. When Erie and I were starting to work together, it was on this DARPA SafeWare program that I alluded to before, which is kind of focused on program obfuscation. And early on, we spent a few years looking at kind of different kinds of advanced cryptographic constructs and capabilities, and various variations of identity-based encryption, attribute-based encryption. I had just kind of transitioned out of BBN, and so I was kind of very focused on problems at the time about access control and things like that as part of cybersecurity. Along the lines of some of the VoIP things I alluded to earlier. And I got really interested in how one could kind of advance beyond the standard RBAC rule-based access control or whatnot with cryptographic level security kind of as it is. And there's a lot of interesting work that's been going on over there. I do see this as something that never really got its due. I mean, I know there's a very active literature on it. I know there's people that are very good that work on it. Um, it's one of these things where I think that if a large funding agency were to be convinced of the value of this, it would definitely be a worthwhile use of funds to kind of go and look and see how we can kind of take it forward for more fine grained access control. This is on the short list of things of, if I were to go to DARPA and I were to go to be a PM, this is something I would love to kind of try to kind of build out kind of more broadly as an ecosystem because I think it's a fundamental construct that kind of proved its worth, conceptually, but the performance isn't quite there for the quantum secure versions of it. And I think, and I might be wrong, and I could be wrong because I haven't really studied the literature in the past few years. Um, but the fine-grained access control that it provides and mirroring that into existing network security systems and taking more of a systems-oriented approach, I think would be nice. And I think this is, like I said, where a lot of kind of modern cryptography kind of, I don't want to say falls short, but doesn't really get its full value. There's really great work building these constructs, and then the transition into application takes more of a systems view. And that systems work is where I think a lot of things kind of fall down in the kind of the cybersecurity ecosystem of transitioning advanced cryptography into cyber secure systems, as it were. So
Yeah, I agree. So one of the coolest features I think with OpenFHE is your key splitting and the distributed signing opportunity. Obviously, it's defined as multi-party computation. So, which application areas do you think might be most useful for this type of approach?
sure. Yeah, there's a few different things that we have been looking at, and there's a few variations of various kinds of multi-party capabilities we've been looking at. One is, of course, some of the medical domain work that we've been talking about as it is, where you have, data coming from multiple places. Another thing that we have also been looking at, which is kind of also a little bit different, is, what if you have an application where you have a lot of distributed compute resources, where you're kind of out in the field, or you're kind of working in a platoon of cars, or kind of like um, you're in some kind of very kind of austere environment, and you have to kind of go around and do things with phones and collaborate with various kinds of sensors with mobile devices. Can you kind of split up workloads? And it's almost like a secure version of what used to be called sensor fusion once upon a
Yeah,
time.
yeah,
And I think it's very interesting, especially as we kind of think about issues of what's called cloud to edge, edge to cloud. Sometimes the DoD calls it fog computing. There's no really kind of good moniker, I think, quite yet for it, other than how do you opportunistically do secure compute with whatever you kind of have available to you at the time. And like I said, this could be, I think it could be kind of nice for applications like smart vehicles is one, particularly with this, kind of smart utility systems is another. Like, how can you start making resource allocation decisions, securely and quickly? And some of the things can be done with very, very simple operations. Some of them a little bit more complicated. But that's kind of something that I've been kind of having in the back of my mind. And I don't think the time is quite right for it because I think you need a little bit more compute or a little bit more bandwidth. But so it is also.
what's good is that MITRE have just developed a new embed 3D risk model, which looks at hardware, software, networking applications. And really, it would be great for device manufacturers to start to be looking properly. I mean, we do research on side channel analysis where the radio waves from a processor give away the cryptographic keys, the
Mhm.
electronic noise, the electrical noise that can feed back. You can actually recover things. And there's lots of things about the secure enclave and so on. So I think, I mean, obviously, one application of this is in a battlefield situation that if you have a number of devices in the field and one of them gets captured, then it doesn't have the full story. It only has part of what you're doing. But if you put all your processing, all your eggs in the one basket, if your adversary gathers that device, they can get everything out of it. So I think that's a natural extension. And if you want to protect IP, again, that's another thing. If you want to shard a user's key, their fundamental private key that they have to identify themselves, then obviously that type of approach is natural. So one of the flies in the ointment is learning with errors. It's been around for a long time and we love
Yeah.
it. It's fantastic. And we build our lattice methods on it. But it has a problem in that it's not provably secure. I may be wrong. Maybe someone's published a paper that says that there's a mathematical proof that learning errors uh, is a hard problem. And I know that for a quantum computer, it's still a hard problem, so that's not a
Yeah.
problem. But there are some worries that somebody tomorrow might come up with a solution to be able to solve with learning errors. And I know that NIST and other standards agencies want another method to stand up. So I know it's a difficult question for to ask. So what's the future of homomorphic encryption? Is there going to be another method that's going to come along to replace Lattice so that we can have a backup, or is Lattice the only show in town?
Yeah, that is. I'll have to defer to my colleagues, Vinod and Shafi and Yuri, kind of on kind of these kind of deeper thoughts on the fundamentals of homomorphic encryption too. Um, and so I frankly, can't really speak to that. I will say kind of something that I say, and I think it's more of a systems view, is I see the future of homomorphic encryption being kind of like, mimicking or the kind of the history of homomorphic history and future of homomorphic encryption, mimicking a lot like the history of general compute.
Yeah.
Way back in the old days, we were kind of programming, with a soldering iron and things like that, kind of like designing early circuits for applications on top of FHE and slowly kind of eking out, higher level assembly languages and compilers and things like that. And if you look at the history of compute, yeah, there's been very different kind of compute models fundamentally that have come around, whether it's like a Turing design that's been kind of like more for theoretical constructs, whether it's a RAM-based model or circuit-based models and things like that. And fundamentally, this kind of notion of kind of layering of abstractions on top of a fundamental compute model, I think is kind of core for what we are doing in at least this current, understanding of fully homomorphic encryption based on ring learning with errors. I do see that as other kinds of constructs come around, I do think kind of fitting into this kind of notion of the pattern of history of kind of increasing level of abstraction is going to be part of it. And, I've kind of taken it to heart that even if kind of something else comes around that's going to be very different, this kind of the story of how we do things is to use a bit of a euphemism, is kind of like rinse, wash, repeat, or wash, rinse, repeat, kind of for what it is. It's a kind of same method of designing high performance compute is by basically starting from the bottom and kind of working your way up as you go with very similar models that kind of been applied for general kind of RAM based silicon processing too, as it is. So,
That's excellent. And obviously you need to look at the problem. And if the problem just involves subtraction or addition, then there's paleo. You can do a
yeah,
square and so on. So partially homomorphic encryption is
yeah.
a perfectly good solution in many applications. And we probably don't need to look to full homomorphic encryption for some things. But obviously the dream would be that we build a processing engine, a compute node that can actually do these things and can encrypt with encrypted data, and we don't have our von Neumann architecture anymore. And I think that's the way things are going, and certainly machine learning is pushing that to its limits. So what does the next decade look like in cryptography? What are the problems that we need to solve? I know we've talked about a few of them already.
Yeah, no, this is a good question. What's the next decade in cryptography overall? I do see, one thing that we haven't talked about that I think is, kind of an unsung hero of modern cryptography is verification systems overall.
Yeah. Yeah.
How do we verify cryptography? How do we basically, show proofs of correctness and these kinds of things? Um, it's something that we've kind of tangentially been involved with through colleagues, through DARPA and things like that, and kind of the advances that are going on over there. Um, I can name drop a few folks, but there has been a lot of really kind of very good fundamental work going on with advanced cryptography and verifying it as it is. And I don't think that area gets its full due kind of for what it is and how important it is. And if I did have kind of a magic wand that I could wave, more kind of applications of verification to implementations and designs of encryption, I think is going to be very important. But that's not a 10-year vision. I know that it's like a 1-year vision kind of for what it is. Although there's a lot of kind of other ongoing verification stuff. Um, what I did do see is one thing that was nice also, Vinod, my partner at Duality and co-founder, uh, he is wonderful to work with. But one of the also nice things about him is he used to sit next to Ron Rivest at MIT, and so I
Wow.
got to chat with Ron every now and then.
Hmm.
And he was telling me like the early history of RSA and RSA protocol and RSA as a company,
Hmm.
and how when they first discovered it, that first start implementing RSA, that the compute at the time was not able to kind of keep up, and government and kind of a few others funded the development of custom ASICs specifically for RSA to accelerate RSA, which nowadays is not an issue because it's we run it in kind of watches and stuff like that even. Um, and eventually things kind of moved out to commodity. And the trend I also see is an increasing commoditization of cryptography, also for what it is. And one of my close colleagues, Drew Dean, who was my first sponsor at DARPA for Homomorphic Encryption, who unfortunately passed 3 years ago. But one thing he shared with me as part of his vision for FHE back in the day was that if you look at fundamental breakthroughs in cryptography, like RSA, elliptic curve, homomorphic encryption, uh, generally it took about 20 years for a fundamental breakthrough to kind of propagate into commodity use. RSA, in the 70s, and it was like in the 90s with the World Wide Web, elliptic curves, Blu-ray players, and FHE, we're just about there. And so I would start to look at, what are the fundamental breakthroughs that happened about 10 years ago that are just kind of getting, into implementation and showing their worth. That's kind of where I would bet right now, kind of for what it is, and whether that's, like I said, identity management systems, zero knowledge proofs, and kind of commoditization of those kinds of things, all fair game. The benefit and drawback of being so focused on FHE is I kind of have my blinders on sometimes. So not necessarily looking at the literature and its colleagues, its conversation with colleagues like you and Vinod and Shafi that I kind of hear like what's going on in the rest of the world. But for better or worse, I'm, like I said, a bit of a tunnel vision for myself, kind of for what it is right now. So
Yeah.
yeah,
And it's for the next decade or so, we're going to see such disruption on the internet. So we have quantum computers breaking RSA and elliptic curve and LGAMO. So we now need to migrate our existing method for TLS, for
yeah,
signatures and for key exchange towards these lattice methods. Luckily, homomorphic encryption is already okay with that because it's robust against quantum computers. So I know it's a difficult question to ask because it's not quite in your domain, but
yeah,
how do you, I mean, there are trillions of public key assets, and every connection to the internet is
yeah.
public key signed, and the key exchange is there. How do you think we're at? I know Biden signed a memo to say that all critical national infrastructure agencies and entities in the US must seek out every bit of public key and have some migration strategy. But how is this going to scale across the world? What's the strategy going to be, do you
Yeah,
think?
no, this is good. This is a really good question. Actually, you got me thinking about, kind of my older conversations I used to have when I was at BBN, with some of the early internet founders about, some of the design choices that were kind of made in the early days around things like DNS or BGP and kind of the early protocols about, the magic number. How many DNS servers are there? 13. Why? I don't know, because there's 13. That's kind of how it is. Somewhat arbitrary and how, for example, DNS was not, was designed very, very well for what it was needed for back then. but it's a bit of a kind of a weak link nowadays in terms of security and scalability and kind of all the things that kind of go on. And I think that's similar with a lot of kind of key management systems that exist right now, is they are kind of deployed, for early versions of applications that didn't necessarily scale to kind of how we do things right now. And maybe, like I said, whether it's like, PGP, GPG, key management, X509, certificate systems and things like that, haven't really kind of kept up with, the advanced needs of, siloing of data, key management of data, and what it is. And, maybe there's an aspect of access delegation that kind of comes into that, about how do you use things like hybrid cryptography to do like, key delegation and things like that. It could even be aspects of transciphering, like how do you basically take something that's encrypted in one scheme and re-encrypt it into another scheme, whether it's a hardware-based solution like TEs or an FHE-based solution for doing things like transciphering also. But this notion of kind of mixing and matching and having secure data flows, I think you're kind of getting at something that's really interesting of how do we break down silos and enable these kinds of flows by either sidestepping or taking advantage of the existing infrastructure that's already there, but not necessarily being limited by these existing infrastructures also. So I would maybe look there. I think it's an interesting question, very interesting question that you're asking. So,
Yeah, I mean, it's a fundamental thing. It needs to happen in the EU, it needs to happen in the UK, it needs to happen in the US, it needs to happen across the world. It doesn't do any good if one part of the world goes post-quantum crypto and the other part is still using the old legacy
yeah.
at all. But obviously, the Googles and the Microsofts will drive a lot of this, and the Cloudflares and companies like that. So hopefully, it will happen, and we'll see this transition. So I know it's difficult, a difficult question, but if there's one thing you could have changed in your career, what would it have been? What thing would you
Oh,
have done different?
it's an interesting question. A close friend asked me that fairly recently also. And in some sense, it's kind of like, hey, I love where I am. I kind of have, I've built lots of good friendships, lots of great partnerships. I'm very happy with community. I'm kind of very happy with my state, my place in the world. So at some level, the answer is nothing. I'm kind of happy with the way things are, but it sounds a little pompous, I think, also. If I had to change one thing, I think that I think I would have probably taken more computer science classes when I was in grad school. One thing I didn't take and I happen to be a professor of computer science, so this is maybe a little bit biased also. I've always been fascinated by programming languages. I've always been fascinated by operating system design. I have no formal training in it, but I just found it really, really interesting also about the notion of compilers and how compilers work, about how operating systems work for resource allocation systems and things like that. And I think I probably would have taken more kind of these systems oriented things much more seriously when I was a student. And my computer science education is very patchy in that, I understand kind of like the fundamentals of math. I understand the logic. I understand the hardware transistors as we were kind of talking about before. And I kind of know the application space of networking, but there's this huge gap that I kind of have in my education that I think I would have kind of done very differently. And maybe being a computer engineer as opposed to electrical engineer would have been a good way to kind of split the difference at some level. But never enough time at university is also kind of the side of it too. But it's always fun to build things also. So yeah.
I think so. I think the perfect degree in this field is computer science and electrical engineering or electronic engineering because more and
Yeah.
more we're moving into the hardware, the transistors, the processor, the embedded systems. And I worry that some of our computer science education is a bit too high level. And where
Yeah.
the real issues are now happening is, as you say, we need to build chips and systems and architect systems that are distributed, that understand the hardware underneath so that you can match to the software. So to me, that perfect fusion is computer science with electronic engineering. It's a shame that we don't attract students. They either go for one or the other, and they don't see the advantage of that crossover of understanding Boolean logic with understanding how to write a Rust program. So my penultimate question, thanks for for spending all this time. I know that you're a busy person. What advice would you give to graduates who are kind of near graduation about the skills and knowledge that they need to pick up?
Right. So yeah, though this is a very easy thing for me to answer. I have very strong feelings on this. Is that be flexible in your career. I see this is slightly biased towards people coming out of their PhD,
Yeah,
but I think it applies also to kind of other degree levels. I see students coming out of school and having this mindset. It was like, hey, I studied this one thing for 5 years. And maybe it's even like, hey, my identity is wrapped up on this thing I've been doing for 5 years. This is what I should be doing, kind of overall. And maybe they kind of also see like their professors kind of in grad school that kind of did one thing in grad school, then got a professorship and kept on doing it. And like 20, 30 years later, they're still kind of doing a lot of the very similar things. And my advice to students is, you know, don't be afraid to kind of go outside your area for what it is. Don't be afraid to kind of shift from engineering to computer science or to, chemical engineering or even some other area. A lot of the kind of some of the best people I've kind of seen in my career have had these huge jumps in what they've done. Uh, for example, Yuri, who's I'm very, very close to, I have just tremendous respect for as an intellectual, and as he is basically fundamentally my research partner for 10 years. His PhD is in chemical engineering, as I alluded to before. And it's something that we talk about regularly, that when we're trying to recruit folks to kind of come into Duality or other things that we're doing, it's like we'll bump into these students and say, well, I've been doing this one kind of cryptography. I don't want to do this other cryptography because that's what I know. And I was like, we're looking at each other as like, I'm a control engineer and he's a chemical engineer, saying, well, you don't want to change the focus of cryptography. Well, let me kind of talk to you a little bit and kind of talk about, flexibility in one's career and one's life. And this is kind of the fundamental advice I give to a lot of students, post PhD. But I do think it's applicable overall. Seek out these things, and don't be afraid of kind of change and what you focus on and what you do overall.
yeah, yeah, I
Yeah,
completely agree. And not to lose your childlike investigation of the world, why is the sky blue?
yeah,
So even though you've learnt a method, that doesn't mean that you shouldn't question what the problems are that need to be solved in our world. So I completely understand. And bringing together two different people, I think Ravesh, Shamir, and Edelman were different people. Ravesh
yeah,
was the kind of thinker of new ideas. Shamir was very much the cracker of his ideas, and Edelman was very much the mathematician. Ravesh was really surprised when he woke up and he had this idea of RSA, and the other two couldn't crack it. He found it really strange because every method they had created up to now, they had actually cracked. If you had the same three people who do the same three things, then that
yeah,
magic doesn't actually work. So I think that team with you and Yuri really works together. A very technical person with someone with a different viewpoint, understanding the real domain and the application of it. Because without applications, we go nowhere with cryptography. And I think it's important to really look in you in the medical field. It's very important that we have privacy. So I think understanding problems and matching it up and creating teams is really important. So I'll come to my very last question. So thank you for taking all this time out your busy schedule. So if you were a new researcher now, you had just finished your PhD, what problem would you don't have to say uh, homomorphic encryption or anything
yeah.
like that. What problem would you try to address?
That's an interesting question. One thing I was very fortunate to do at early in my career post PhD was to kind of get into this DARPA ecosystem where it's very sink or swim, kind of focus on things that are value of the moment. And sometimes being able to kind of hitch your wagon to kind of new things that emerge. And DARPA has an interesting philosophy about what matters for research. They look for either new breakthroughs that happen and trying to understand how to capitalize on them. Like FHE was a new breakthrough at the time that they wanted to capitalize, or there's kind of an emergent, national security issue that drives research also. for example, after the kind of U.S. military was in Iraq and Afghanistan, IED and brain damage was traumatic brain injury, excuse me, was a major thing that was not a problem before. And so these kinds of dueling, like being driven by breakthrough versus being driven by emergent problems, is an interesting approach. And then you see people in DARPA community, and you have some folks that focus on certain kind of problems, and they'll use any kind of techniques, but they'll focus on a problem. And you have other people that are like super exquisite understanding of certain techniques, and they'll apply it like everywhere, kind of for what it is. Um, Coming out of my PhD, if I had to do it again, I would, focus more on, what are the emerging problems that kind of exist in the world as they are, and what does it kind of, mean to kind of focus on these things and whatnot. And some of the problems that I kind of see fundamentally that are emerging is, there's it's very easy to kind of say something very high level like world hunger or kind of cancer or these other kinds of things. But I've been very interested in, and this is from some of the medical exposures and talking with Sasha Gusev at DFCI was some of these bioengineering type techniques of CRISPR, and they have various kinds of compilers that are kind of coming out for designing custom proteins and things like that. This notion of applying computing abstractions to biological methods, I just find fascinating in terms of just design of proteins and things like that. There's I've had a few colleagues that have kind of focused on this, and it is really a very kind of synergistic. Like, you got to know the medical, you got to know how to do compute, you got to know how to do applications and all these different kind of things, and you have these just amazing teams that kind of come together to kind of be successful in the area. And I find that fascinating. If I had another lifetime, I'd probably, go and spend a little bit of time on that one also. But I do find that very interesting overall as it is. So,
That's great. It was so good for you to talk about BBN, and when you think about AT&T as this massive monopolistic company, and they were just so blasé. Oh, this packet switching thing is
yeah,
how can they compete against our TDM systems, and it'll never work and so on. And then they saw the potential, the company saw the potential of the packet switch devices, which I think it was UK, US development
yes,
that happened in there. And then you've obviously got people like Vint Cerf, who was creating these RFCs. And at one time, an RFC wasn't an electronic document, it was stamped addressed envelope. You actually used to have to send the RFC out in the mail to people. But that built the internet. I mean, if there's one thing that's really changed our world completely, it was DARPA and DARPANET. And without that, would be somewhere completely different than we are now. So it's really amazing to hear that company. I think they were taken over by a defense company eventually. I forget the name of the company, but it wasn't Lockheed Martin, was it?
yeah. A few years ago, they were acquired by Raytheon.
Raytheon,
They still,
that was
yeah,
it. Yeah,
they still exist as an entity, and I still
yeah,
have a lot of close colleagues there. They're
yeah.
still in Cambridge, still do their thing.
Mm.
And yeah, no, I definitely bump into the folks from that organization, fairly regularly. So they're not necessarily as prominent because they don't necessarily have the same website anymore.
Yeah.
But thankfully, they still exist as an entity also, and it's still a very dear place to me. So
And you could say before that time, we had the ISO and OSI and the IEEE and the standards
yeah,
body, and every country fought with each other, and it would take years for any standard to happen. And then
yeah,
the RFCs came along, and we had a dynamic way of the expert in the field just publishing something, and everybody kind of agreed to it. So I think
yeah,
that to me sounds like the open source versus the monolithic closed source world. Uh,
yeah,
and that's what you're really driving forward, to make sure that everybody can actually adopt, they have the chance, every opportunity, every new researcher can actually add lines of code, and we build a better world of software which is more resilient, more secure, and hopefully more private in the future in its application. So thanks very much and enjoy the rest of your day. You are where are you in the world just now?
I'm in the part of New York City that's called New Jersey, so just
Oh,
over the river from
beautiful.
the city. Yeah, yeah,
Yeah,
yeah.
yeah. Well, I'm in Edinburgh, across the pond, as you would say. So hopefully, if you ever come over to the UK, we'd be happy to host you in Edinburgh, a beautiful city, just like New York, a little smaller. But we would love to have you over here. We have a great ecosystem of companies into cybersecurity and cryptography, blockchain, and so on. And we're really happy to collaborate with US-based companies. So thank you and enjoy the rest of your day. Thank you.
Thank you, Bill. Happy to be here. Thanks for your time. All good.
Thank you.